In this paper, we propose a novel personalized face generation framework, capable of simultaneous identity expression control and more fine-grained expression synthesis. The proposed framework takes 3 inputs: a prompt describing the background, a selfie photo uploaded by the user, and a text related to the fine-grained expression labels. On the output side, the generated face will have the same identity as the input selfie photo, show the expression specified by the text, and be placed in the background described in the prompt. We replace the input expression label with 2 other labels, dismay and grief. The expressions in the generated faces are precisely controlled by the input expression labels. We show another example. Here we show the pipeline of the proposed framework. The prompt that describes the scene will be input to a pre-trained text-to-image model, Stable Diffusion, to get the background image. The text that describes the expression will be used as the search key in the 135 class emotion dataset to retrieve the expression image. Together with the input identity image, the 3 images will be used as conditioning in a diffusion model to generate the result. We named the novel diffusion model as diffSFSR, which can conduct simultaneously face swapping and reenactment. We show the pipeline of the proposed diffusion model, diffSFSR. The training of diffSFSR consists of the diffusion process and the denoising process. In the diffusion process, the input IBKG is firstly embedded to a latent Z0, and then be added with the Gaussian noise in the diffusion process. The denoising process denoise the latent ZT at random t time step to Z0, by using 2 times the UNet conditioned on the masked IBKG and extracted features from IID and IEXP. In the inference phase, the trained denoising UNet is used multiple times to gradually generate Z0 from the Gaussian noise ZT. To realize the goal of simultaneous face swapping and reenactment, we propose 3 innovative designs in the conditional diffusion model. Firstly, we develop the identity and expression encoder, which are competitive with each other, to reduce the transfer of residual identity attribute in the expression encoder to the final result. Secondly, to achieve both efficiency and accuracy in imposing the identity and expression constraints during training, we propose the improved midpoint sampling, which can generate the face of higher quality with only 2 times of prediction than the original midpoint sampling. Thirdly, we explicitly provide background condition in the training phase, so that the diffusion model can focus on the generation of face but not background, and get more hints from inputs to recover face pose and lighting. This design is different from previous methods that use background image only in inference, and proves to be more effective. We show our fine-grained expression synthesis results, which are controlled by 135 expression labels. To the best of our knowledge, there is currently no face generation or manipulation method in academic or industry can reach this level of fine-grained expression control. We compare our method with the SOTA open-source text-to-image model, Stable Diffusion XL. Compared with our results, SDXL can't synthesize the accurate expressions corresponding to enjoyment, anxiety, or grief. The dilemma faced by most text-to-image methods is that they can only recognize a few limited expression labels. Comparison with hybrid method. As there is currently no method that can perform simultaneous face swapping and reenactment, we construct a hybrid method as a potential competitor by directly combining the best face swapping method in terms of ID score, SimSwap, and the best face reenactment method in terms of EXP score, style heat, based on our quantitative comparisons. Our method can produce more accurate expressions and poses than the hybrid method. Comparison with face reenactment methods. Our method can conduct the face reenactment task by setting the inputs IBKG and IID as the same image. Compared with face-to-face and style heat, the expression in our results is more similar to the source, and the identity and pose are more similar to the target. Our method can also conduct the face swapping task by setting the inputs IBKG and IEXP as the same. Our results are more similar to the source faces in terms of interfacial features, such as beard. There are obvious artifacts in the results of hi-fi face. The faces generated by E4S do not blend well into the background, leading to less natural results. In addition to expression preserving, our advantage over SimSwap is that our method can generate faces with better image quality. We compare 3 sampling methods: one-step sampling, middle point sampling, and our improved middle point sampling. In terms of identity preserving, our sampling methods can produce more facial details, such as wrinkles and whiskers, thus more similar to source B. In terms of expression preservation, our result in the third row exhibits less angry expression, thus being more consistent with the expression in source A. In the fourth row, our result displays the expression of slightly opening mouth better than others. The left figure shows the reconstruction errors produced by different sampling methods. All sampling methods can decrease the reconstruction errors along with the training steps increasing. Our sampling method can achieve lower MSE than others in all periods. The right figure shows the image reconstruction results by denoising XT using different sampling methods. Our results are not only more faithful to ground truth X0, but also more realistic and clear in the regions of eyes, mouths, and even the reflection of sunglasses. In the ablation study, we demonstrate the effectiveness of the background conditioning and the compound identity embedding. The generated faces without background conditioning suffer from inaccurate lighting, exhibit more face pose errors, lack seamless blending with background, and are comparatively more blurry. As shown in the first, second, and third rows in the figure, each time we remove an identity embedding, the generated faces become more similar to source A in terms of identity, and less similar to source B, which provides the expected identity. In the fourth row, the inadequate identity representation even incorrectly puts glasses on the results.